Work power energy. Work, it is defined as the product of force and displacement of the point of action of the force parallel or anti-parallel to the direction of force. It unit is joules. Already I have told you about dot product. So now your work is written as F dot S, where F is the force, S is the displacement. F is the force and S is the displacement. Displacement. I use the word displacement. Displacement. Now see, I have said that the product of the force and displacement of the point of action of the force parallel or anti-parallel. Supposing the force is in this direction and the displacement is also in this direction. Force, displacement is in this direction. Then under that case, they are both parallel. So Fs cos theta, cos 0 it will be, because at that time uh, theta would be 0 because they are parallel. So this will give me work equal to Fs. Now anti-parallel, I have used the word anti-parallel. Suppose there is a frictional force being applied here and the displacement is done, then what is the work done by the frictional force? This is Fs cos 180, and because they are anti-parallel, therefore theta is 180. They are just anti-parallel to each other. So work will be minus a negative, negative of Fs. This is Fs. Now this is what it means by parallel or anti-parallel. Now the next point is work is done only when the energy of the body changes or due to force or torque. See, the proper full expression of work is F dot S and plus or minus whatever it will come. It is torque with a change in small angle theta, small angle, very small angle. Big angles are not considered vectors. Very small angles are considered. This is the total expression. But you only need in your syllabus F dot S. You don't need this. You don't need this expression. You don't need this total expression. Now, here I have written that work is done when you are lifting a book. See, when you are lifting a book, you are lifting a book. In this is the book. This is going up. You are applying a force. F applied is in this direction, and the displacement is also in this direction. But the gravitational force, that is F G, if I write it this way, this displacement and this gravitation are opposite. Gravitational work done by gravitational G would be minus FGS. Whereas your work done by applied, I'll write here applied is equal to FAS, applied force into S, because they are now parallel. The concept that I used here and the concept that I used here. That is why. Now, physical work, and there is something called useful work. You can read the definition. Now, see, physical work is the work that you do. Suppose, so we will work on the work energy theorem still little later. Very important theorem, and this most of the time comes in the external examination. Now, before that, let me tell you what is useful work and what is physical work. Suppose you are carrying a bag in your hand and moving in circles. Moving in circles. You're carrying a bag. This is you carrying a bag and moving in circles. So the work done at that case is zero. Why? Because the displacement is zero. Because the displacement S vector is zero. That's the main reason. This is just physical work. You will get tired. Nothing, though no change in if the energy will change or the system will change. But when you are lifting this book, up, then the energy of the system is changing. That is called useful work. I hope you've understood this, what is useful work and what is physical work. Now, after this, we will get into the most important thing, that is the work energy theorem. We will discuss work energy theorem in great details.